Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. Today we're taking a deep dive into one of the most beautiful and actually one of the most important concepts in Unit 12, atoms. We're going to be talking about the line spectra of the hydrogen atom. And our promise, as always, is to demystify this, to make it so simple that you'll understand it perfectly for your exams. So let's not start with a textbook. Let's start with something you probably see every day. Think about those street lights. The ones that glow with that really intense bright yellow light, the sodium vapor lamps, or maybe fireworks. You see those brilliant greens or the deep reds exploding in the sky. Why is it that when we excite different elements, they always, and I mean always, glow in their own specific signature colors? Why not just a continuous white light like you get from a regular hot bulb?
That is a very interesting point. I mean, we see the hydrogen discharge tube in the lab, and it glows with a very distinct red color. My assumption was always that, the sheer heat or the high energy we were passing through it simply makes the atom hot. And that heat that decides the color, is it the temperature that's the main thing, or is it something else?
That is an excellent question. And actually, that's where the whole revolution in physics really begins. Many people have that same classical idea. Hotter things just emit brighter light, maybe whiter light. But here is the really surprising, the counterintuitive fact. The specific color, or let's say the wavelength, of light that comes from a gas is determined almost entirely by the element's atomic structure.
The structure itself, not the temperature.
Not primarily the temperature. For example, that specific yellow of sodium is its unique atomic fingerprint. It's not about how hot the flame is, it's the fact that it is sodium. This idea, this fingerprint, is the clue that allowed us to finally unlock the internal design of the atom. It's so powerful.
So this is how astronomers know what stars are made of.
Exactly. This technique, spectroscopy, lets them analyze light from the distant sun and say, that contains hydrogen and helium, just by looking at its colors. Okay, so let's unpack the core idea. Let's say we take the light from these excited atoms and we pass it through a spectrometer, which is like a very, very precise prism. We don't see a continuous rainbow. Not at all. Instead, we see something amazing. Just a few discrete, very thin lines of color at very specific positions.
And in between them.
In between them. Wide, dark gaps. No light at all. We call this pattern the atomic line spectrum.
So if a continuous spectrum is like a full rainbow, then an atomic spectrum is like a broken rainbow. Or maybe a barcode made of light.
A barcode is a perfect analogy. It's a unique barcode for every single element. And this observation is just monumental. It tells us that atoms emit light only at specific allowed energies, which means energy inside the atom is not continuous. It's quantized.
So this is the proof that classical physics was wrong, right? Because classical physics said the electron should continuously spiral inwards and give off a continuous spectrum of light as it loses energy.
Precisely. The observation of these sharp lines is the direct experimental evidence that Rutherford's model had a huge problem. We needed a new idea. And this is where Bohr comes in. To visualize his idea, let's use our main analogy for today. Think of the electron orbits not as a smooth ramp where you can stand anywhere you want. Instead, think of them as rungs on a ladder or steps on a staircase.
Okay, so like fixed positions.
Fixed, discrete energy levels. An electron can only perch on these specific rungs. When it gets excited, it absorbs energy and jumps up the ladder to a higher rung. And when it falls back down, say from a higher step, E upper, to a lower step, E lower, it instantly releases that exact energy difference.
And that energy difference comes out as light.
It comes out as one single packet of light, a photon, which corresponds to one of those specific lines of color in the barcode.
Wait, but how can it be instantaneous? If it's at n equals 3 and then suddenly it's at n equals 2, how? Doesn't it have to travel through the space in between? That's really mind-boggling.
And that is the beautiful mystery of quantum mechanics. We call it a quantum jump. Bohr's model doesn't explain how it happens, only that it must happen instantly between these fixed, allowed rungs. There is no in-between level. It's that sharp, distinct jump that creates the razor-sharp line in the spectrum, not a blurry wash of color. Now that we have the core idea, quantization, the staircase, the jumps, let's get to the formal definitions. These are crucial for your theory paper. Could you please read out the formal insert definition for the emission spectrum?
Of course, it says, when an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, the emitted radiation has a spectrum which contains certain specific wavelengths, consists of bright lines on a dark background. The spectrum emitted by atomic hydrogen is shown.
Thank you. So those bright lines on the dark background, those are the photons from the jumps. And for hydrogen, these lines are not random at all. They're beautifully organized into systematic families. We call them spectral series. They're categorized by where the electron finally lands, its final energy level, which we call N final, or NF.
So the destination matter.
The destination orbit decides everything, and we have to know the three main series. First up, the Lyman series. This is when the electron takes the biggest possible jump all the way down to the ground state, NF equals 1.
The lowest rung on the ladder.
Exactly. And because the energy difference is so huge, these photons are very energetic. They fall in the invisible ultraviolet, or UV, region. Next, we have the most famous one, the Bohr series. Here, all the transitions end on the second orbit, NF equals 2.
And this one is visible, right?
This one falls exactly in the visible light region. This is the reason we can see that characteristic red glow of hydrogen. And finally, the Paschen series. Here, all transitions end on the third orbit, NF equals 3. These are much smaller jumps, so the energy is lower. These lines fall into the infrared, or IR, region, also invisible.
So practically speaking, since Lyman is UV and Paschen is IR, was the Bohr series the only one that early scientists could actually study because they could see it?
That is a very sharp insight. And yes, historically, the Bohr series was the key that unlocked everything. A Swiss school teacher, Johann Bohr, found a simple mathematical pattern for these visible lines, H alpha, H beta. Even before Bohr had a physical theory to explain it, it was astonishing. And the mathematical model that describes all of this for every series is the Rydberg formula. It's a blueprint of the staircase. The formula is 1 by lambda equals RH into 1 by NF squared minus 1 by NI squared.
And that RH is the Rydberg constant.
Yes, the Rydberg constant. It's not just some random number. It beautifully packs all the physical constants of the hydrogen atom-like electron mass, charge into one precise value. This level of precision, predicting these exact wavelengths from fundamental theory, is exactly the kind of thing we love to simplify here at ProfSam.com. Just a quick reminder, this concept explainer is from ProfSam.com, that is ProfSam.com. So let's actually use that formula. Let's take the most famous line of all, the red H alpha line. This is the line that gives the hydrogen tube its color. It occurs when an electron falls from the initial orbit Ni equals 3.
Down to the final orbit, NF equals 2.
Perfect. So when you substitute Ni equals 3 and NF equals 2 into the Rydberg formula, the calculation gives you a wavelength of exactly 656 nanometers.
And 656 nanometers is precisely red light.
Exactly, red light. This perfect match between Bohr's theory and what was observed experimentally is why the model was such a massive achievement. It proved that energy levels are discrete and organized. This organization is why atoms are stable, and it forced us to accept the quantum world. All right, now for a very important section. Let's tackle the silent killers. These are those small conceptual mistakes that can cost you crucial marks in the exam, even if you think you know the theory. So, misconception number 1. Continuous versus line spectra. The wrong idea is that students think any hot gas emits all colors, a continuous spectrum, just like a hot piece of metal. They confuse the two. The correct idea is this. Hot solids emit continuous spectra, but hot gases, which have isolated atoms, emit line spectra because their energy levels are discrete. A good way to remember is solids give continuous spectrum, gases give line spectrum.
Okay. So it's because the atoms in a gas are separate from each other, they can only make their specific jumps. But in a solid, everything is interacting, so it's all blended together.
You've got it perfectly. Now, misconception number 2, the origin of multiple lines. The wrong idea here is that when students see multiple lines like H alpha, H beta, they sometimes think they must come from different elements, maybe impurities in the hydrogen sample.
They think different colors must mean different elements.
Exactly. But the correct idea is that all the Bohr series lines are produced by the same hydrogen atom, just making different transitions. H alpha is the jump from 3 to 2, H beta is the jump from 4 to 2. Different jumps, but the same element. So the hook to remember is one element, many transitions equals many lines. Now, to really lock this knowledge in for life, let's use a couple of strong memory anchors. First, a simple mnemonic for the series order. Just remember the phrase, Lyman 1, Bohr 2, Paschen 3.
Lyman 1, Bohr 2, Paschen 3. Simple enough.
It reminds you of the final orbit, NF, that defines each series. And the general truth, always remember, line spectra are atomic fingerprints. Next, a physical gesture. This really helps. Imagine that staircase again. When you're revising and you talk about an electron transition, make a sharp, distinct movement with your hand from a higher level down to a lower one. This reinforces the idea of an instantaneous, discrete quantum jump, never a smooth slide.
Right. A jump, not a slide.
And for a bit of a funny association, think of that red H alpha line. That specific red light is hydrogen's atomic destiny. Its fixed energy levels completely forbid it from randomly emitting pure blue or pure yellow light. It's bound by quantum rules. Okay, let's finalize this deep dive with the three most crucial exam-safe takeaways. You must retain these. Point number 1. Atomic spectra consist of discrete lines, not continuous colors. And this provides the direct experimental proof that energy levels inside atoms are fundamentally quantized. Point number 2. The lines are organized into series, Lyman, Balmer, Paschen, based on the electron's final state, NF. And their wavelengths are perfectly predicted by the Rydberg formula. And point number 3, the Balmer series, where NF is 2, contains the visible lines, like the famous red H alpha from the 3-to-2 transition. This makes it the most easily studied series. So this deep dive really shows how just looking at color, just color, drove one of the biggest revolutions in physics history. And now, here's a question for you to ponder. If Bohr's model was so successful, so perfect at predicting all the hydrogen lines,
Why did it completely fail when physicists tried to use it for complex atoms like helium? Think about that. What's the difference between 1 electron in hydrogen and 2 electrons in helium? For now, to get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes. Study hard, and we will talk soon.